open. Ricky, you're sitting down. Mouth, it's time to close him. Yesterday, what was the very first parent function that we talked about? The easiest one. Linear. All right, hold on. I want us to go back to that linear one. I want you guys to label a couple things for me. Ready? To help us get ready for section 1.7. To get ready for section 1.7. Okay. Basic linear functions. Go ahead and use y equals x. It's kind of the easiest one, I think. Y equals x. He has a positive 1 slope centered at the origin. Pretend that's actually on the origin. There he is. Okay. What's one important point of the line y equals x? 0, 0. No, just important points. What's another important point?
1, 1.
1, 1.
2, 2.
2, 2.
3, 3.
How often or how long can we keep going?
Until you feel so lazy.
All right, boring, right? Uh-oh, negative 1 what? Negative 1.
Negative 1.
Okay, hold on. Keep going to the quadratic. Stop. Okay, label a few more points of the parabola. We labeled 0, 0. What's another point?
4, 1, 2.
4, 2? No, that's not right. 1, 1 is 1.
2, 4.
2, 4 is 1.
Oh.
Because
3,
2
9.
plugged in is squared. 3, 9 would also be on there, but let's go backwards. Negative 1 would be, because negative 1 squared is a positive 1. Negative 2 would be at,
4.
so we can see that symmetry, right?
Yes.
What kind of symmetry again? Y-axis, aka an even function. Let's keep going. Cubic. Huh? He didn't go. Alright, we already labeled 0, 0. What's another important point? 1, 1. Oh my goodness, they all have 1, 1.
Negative 1, negative. Wow.
Negative 1 what?
Negative 1.
Uh-huh. Because a negative cube stays negative, unlike a squared function or a quadratic function. Yeah, he'd be way up here somewhere, right? About there? 2, 8, and similarly negative 2, negative 8, because a negative cube stays negative. All right, we have another point. Let's keep going. Square root function. We have 0, 0. Give me another one.
2, 2. 2, 1.
Not 0, 1.
3, 2.
1, 1. Why? Square root of 1 is? Something that theoretically should be easy and yet is hard for some of us.
Like
that
3,
2.
that 3, 2.
4, 2. Why 4, 2?
What?
9 and 3 to 4 is 2.
Square root of 4 is 2. Remember, we can plug it in, plug it in.
9, 3.
9, 3, 16, 4, etc., etc., etc. Right?
8.
Okay. Where did we end yesterday? I think it was this one.
49.
All right, focus on that. 0, 0. Is it a special point? No. How come? What is going on at x equals 0?
Nothing.
Oh, well, kind of.
Yeah, the horizontal.
Nothing described by
Asymptote.
a vertical asymptote, and then at y equals 0, nothing defined by a horizontal asymptote. There's nothing going on at 0, but as we approach 0, oh my goodness, I'm going into chapter 12, I should stop. But as we approach 0, well, that's a different story. Chapter 12 is the last chapter, by the way.
Oh, it's the only chapter.
Approach is an important word for that chapter. We'll see if you remember that at the end of the year. Let's come back. Probably not, but I'll just reteach it. Oh, tomorrow's Saturday. Who remembers anything on a Saturday? Okay, coming back. So what's the point that we can put? Oh my goodness. Do you guys see it? Who's that? He's 1, 1, 2. That's weird.
1, 1, 2.
Also. 10 here. Keep going.
2.
What else?
2, 1 half.
2, 1 half.
2 halves?
3, 1 ninth. No, not 3, 1 ninth. 3, 1 third. That's awkward. Hold on. What would be a point on the other side?
1.
1 half would go where?
1, 3, 3, 2, 1.
Why would 1 half go to 2?
Plug it in, plug it in.
Uh-huh. And when you have 1 over a fraction, what does that mean? Reciprocal, right? So 1 half would go to 2. Wait a minute. What happens as I keep going in? 1 third would be 3. 1 fourth would be 4. 1 tenth would be 10. What's going on to my y values? Increasing without bound. Hence why there's a vertical axis. Yesterday we talked about domain and range. We talked about slopes. Are they constant or are they changing?
Changing.
Yeah, how come? Have you guys figured out why or when we can say the slopes are changing? Whenever the function is
Exponential in any way.
no, not exponential anyway.
Growing.
It's not linear.
Interesting idea. Not growing, because lines grow.
Linear.
Doesn't have a s-
What?
When it's not linear.
When it's not linear. What's another way of describing not linear?
When it's not straight.
When it's not straight. When it has, instead of let's going with a negative, let's go with something that's positive. Let's go with something that is true instead of saying what's not true. Whenever the graph has a
Exponent.
wavy, let's try to be a little bit more.
It's kind of curvy.
I heard it.
Kind of curvy.
Okay, concavity, kind of curvy. Can we just say curved when there's a curve to it? So there's some sort of curve. Anyway, kind of curvy. We'll go with that. Anyway, the slopes are changing.
Or does it have the same radius?
All right, hold on. What else do we got? All right. What is this function strictly doing in terms of increasing, decreasing, or constant? Focus? Yeah. Increasing, decreasing, constant. What's going on?
Oh,
Left or right?
decreasing.
Decreasing from, isn't it kind of strictly decreasing? It's only decreasing? What intervals would we give, though, technically, for the decreasing? Review. That's a colon, even though it doesn't have it. How far left does it go? Negative infinity. We okay? How far right does it go in that decreasing branch or portion? To 0. And then I could say, hey, but it keeps decreasing from 0 to infinity. Why did I not say negative infinity to infinity? Forget. Yeah, Haley.
That would be decreasing past 0.
Yeah, we'd be saying it's decreasing through 0, but it can't go through 0. There's a vertical asymptote. So we have to exclude him. And how do we exclude him with interval notation? Separate at 0 with only parentheses, right? Not including? Not including. Okay, I think that's enough of this page. Let's go to the last page. Yesterday I said we had one more page to go, but it actually has a couple functions on it. The big category is piecewise. The big category is piecewise. But two very special piecewises that are actually kind of hidden piecewises are the step function and the absolute value function. We technically don't need all this room.
Yeah, technically.
Technically. Good word. Let's shorten it down a little bit. Piecewise functions, man, they can be so varied. Because all it means is put together different pieces of functions. They can have lines, they can have curves, they can have parabolas or cubics. They can have fractions, like rational functions, which we're not even talking about yet. So I can't necessarily give you solid characteristics true for every piecewise function. I can't do it. But what I can say is the domains are separated by inequalities. The domains are separated by inequalities. We know that hopefully from the graphing calculator handbook and from a little bit of work we did plugging into a piecewise in sections 1.1 to 1.5 somewhere. They're separated by inequalities. And remember, I think it was also on your quest. If I have f of a particular number of a piecewise, I have to test where to plug it in, which piece, because it only should work in one place, because each x is only paired with one y. So the domains are separated by inequalities, and long story short, for all the characteristics, we have to consider each of the pieces, right? That's kind of obvious, but it's just a quick explanation as to why I'm not giving you definite characteristics for piecewises, because they change. They're different depending on what's in the function. Piecewise is just a general category. So instead of talking about all piecewise functions, I'm going to go ahead and zoom in on two very particular ones that don't look like piecewise functions. They're kind of hidden. If you guys can't see the light blue down here, I think last year you might have seen it with just one bracket. Our book is going to use 2 brackets to set it apart to make it obvious for the step function. Does anybody remember the really technical term for it? Starts with greatest. I didn't see it last year. Greatest. Okay. It's been a while. And maybe you guys actually called it the step function for all I know. Integer function. Does anybody remember what an integer is? Let's see, there's
Any positive or negative
natural.
number?
Any positive or negative whole number, yes, I do. AKA no fractions, no decimals. In the sense of no number with fractional pieces or decimal pieces. Because we could write a whole number as like 5.0000, but the decimals don't mean anything. So greatest integer function, meaning you plug in any number. If you guys notice, it connects between 0 and 1. If it connects, that means for x is 1/2, we're allowed to use 1/2. But guys, what happens if you plug in 1/2 and we ask the question, what is the greatest whole number inside of 1/2? You see the y value? Where is it at? Oh, I should use red. And now I just made it simple. Let's go forward and backwards and it should zoom in a little bit. There we go. So the point would be 1/2, 0. Why? Why is it 0? What's 1/2 as a decimal? 0.5, right? So if we're asking ourselves, what is the greatest whole number in 0.5? Is 1 in there? No. Now don't we naturally usually round to 1? There's like this whole rule you've learned of since you were itty bitty, right? Well, not itty bitty, anyway, smaller. It doesn't contain 1. It's not enough to have 1. But what is contained in 0.5? 0. So what if I was to pick another point? What if I was to pick something like 2.9? Oh my goodness, we should totally round that to 3, right?
No.
What's the greatest whole number in 2.9?
2.
2. This is a special function. You're not rounding like you're used to. You're actually, in a sense, rounding down. But it gets kind of funny as we go to negative numbers. Let's say we have negative 2.1. Your brain, based on what I just showed you, probably say, what's the greatest integer?
2.
Negative 2.
No,
But you're wrong. Because if you look at the graph, where is negative 2.1? At negative 3. Whoa, 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 whoa. These are like behaving totally differently, right? Think of a number line. Here's 0. Here's 0.5. How did we round it? Down. Backwards. What if we went to 2.9? There's 2, there's 3. Some of you are like, oh, I get it. Hold on. 2.9, where did we round it? Backwards to 2. Now, what if we had negative 2? 0.1. Where do we round it? Backwards. The exact same thing, but negative numbers are a little strange. Because what's on the left of negative numbers? Higher negative numbers, because it's more negative. And maybe that's why some of you have always had issues with adding or subtracting negatives and positives. Think of a number line. I don't know. In my mind, it makes more sense. Or memorize the rules about like who's stronger and we're winning in a fight. I don't know, and keep that sign. Absolute value. Let's talk about him. Y equals, all right, he's indicated by the 2 straight up and down lines. We already talked about him in the graphing calculator handbook. Where is he found if we are using our calculators? Math, and then go over 1, right? And then abs, I think. Older calculators, it actually says ABS and has a little parenthesis. Oh well, put it in. Newer calculators are like, yay, straight lines, either way. Absolute value. What does absolute value do? Give me some important points. We have 0, 0, right? What else do we have? 1, 1.
2, 2.
Plug in a positive, get out a positive of the same. Plug in a positive, get out a positive of the same. Okay, this all behaves one direction. Now, hold on. as a piecewise. It's technically a piecewise function, but they did this cool little notation to shortcut it for you a long time ago, and now it kind of messed you up because you don't realize what the pieces are. You do it, but you don't know how to deal with it as an equation. What numbers, what kinds of x's was I choosing, not backward, I'm only one person, was I choosing as I went to the right? Positive. So I'm going to say it's going to behave a certain way for all positive numbers. So, okay, obviously, if one piece is all the positive numbers, I could even make it equal to 0 in the sense that it kind of behaves the same way. What would be the other piece? What would be the domain for it? Yeah, we're going to go to all the others, or all the less than 0. Okay, now we need to describe with an equation what happens without using the straight up and down bars. When we plug in an x that's positive, did it change? No, it stayed there. Oh, so if x is 1, plug it in and you get 1. If x is 2, that fits here, plug it in, you get 2. If x is 3, plug it in, you get 3. But what happens as we start going over here? What point is that?
Negative 1, 1.
Negative 1, 1. Uh-oh. Can I just write for negative numbers x again? Because that would be a negative 1 fits here. Negative, it's not negative, it's positive. Mathematically, how do we change a negative into a positive? Multiply by negative 1. Or divide, but multiplication is so much nicer. Now, if I was to give you that at the beginning of class and say, is it true? You're like, no, it's not. Absolute value can never equal a negative. It doesn't. But does absolute value with a negative number have to be opposite that negative? Yeah. So plug in a negative 3, negative 3, oh, that's a positive 3. Oh, hey, that's what absolute value does. Absolute value is a hidden piecewise function. Now, a couple other things about absolute value. Because the step function, we could go back to him just for a second and say, hey, is he a hidden piecewise also? Yes. But how many pieces would we have to define? Yeah, we're not doing that. But absolute value only had 2 pieces, so it was a little bit easier. What's the domain of both of these functions? What can we plug in? Negative infinity to infinity for sure for the absolute value. Some of you are like, there are holes. True. But even though there's a hole at 1, there's still a point at 1 also. So technically 1 has a point, 2 has a point, 3 has a point. So technically step function has a domain of all real numbers also. What's the range of absolute value? How low does he go? 0. Right? And above. So we could say greater than or equal to 0. Or with intervals, what could we say? 0 with a parenthesis or a bracket. Does it get there at 0?
Yeah, yes.
So we can say a bracket. Then how high does it go? Infinity. And remember, why do we always put a parenthesis around infinity?
Because it's an idea.
It's an idea, not a number. We can never get there, so we can never put a bracket. Sorry, get your notes out, or else I'll send you your office if you're not wanting to participate. Okay. Let's come on back. What's the range? This is a little bit harder. What's the range of that function? It does go forever low, it does go forever high, but what's the problem of the ranges? What y values does it hit?
Only the whole numbers.
Only the positive or negative whole numbers. Wait, what was the name for the positive or negative whole numbers? Integers. Right? So we could say that y is within, we could say the set of all integers. And technically the way that we say that is, hold on, I have to remember what the symbol is. Yeah, I thought it was I was making sure it wasn't the I, but it's not. It's like a double Z, like how the double R is for rationals, the double Z is for integers. I guess you could call it a slanted I. But anyway, all counting numbers. Question. What are the slopes? Or what is the slope of the step function? 0. Every single piece is flat, right? And flat is horizontal, and horizontal has a slope of? Interesting. So all slopes are 0. What's the slopes of the absolute value? The last thing we're going to write for these. What are the slopes of absolute value? Changing.
1 and -1.
There are only two slopes. One piece has a slope of, look at it, -1, right? mx plus b. One piece, this one, has a slope of down 1 over 1, or -1. So for the, we'll say, for x within, what would that be, -infinity to 0? Keep it open. M equals -1. And for x within, on the other side, 0 to infinity, what would my m be? I'm too tall for this board. 1. Sorry, I got slanted. But how do we know that the slopes are actual numbers? Because they're not curved, right? Whenever the function is curved, then the slopes are changing with those funny tangent lines, and I said something about calculus, and we probably all tuned out after that. All right, we are at the end of section 1.6. Wait, that's not homework 5. What is it?
Homework 6.
Typo, what's the answer? Section, that doesn't make sense either. All right. Look at the backboard though. Finish 1.6, check. Now what are we doing? Woo! All right, now hold on. You don't want me to cram this into Monday, right? You don't want me to cram it into Monday, so let's get some covered today. We'll have a weekend to kind of recuperate, and then Monday we'll come back and finish. And some of you can start 1.7, most of you should. Start 1.7 homework this weekend because you're like, it's going to be a beast. And it kind of is. But it's something that you've seen before. If you're smart and kept your Algebra 2 notes, you could actually go back and review it with those notes, and have my notes, and have our book, and have random things like Khan Academy online that might help you.
No, that's no comment.
No? Patrick J. and T. Done.
Okay.
Okay.
After Mr. Hart, we don't.
Yeah, we're gonna go watching Khan Academy again.
Does he just show it in class?
That's all he's did.
Anyway, shh. Don't talk about other teachers. Okay. We're recording. Okay. Section 1.7. Transformations of functions. You guys can see one up here. He's the easiest one, and there's a lot of words. Do you need to write them all? No. You don't need to write them all. You've seen this before. But you do need to remind yourself of what's going on. So for the little formulas down below, C is a positive real number. If he was negative, then this would mess everything up. And if he was a complex number, well, yeah, that wouldn't really apply. But translations are shifts. Shifts do not change, do not distort, do not change the shape of the graph, right? They don't change the orientation and they don't change the shape. Shifts merely maintain the shape and move it to a new location. Now, the way I like to remember all the transformations and which ones go with which, besides just memorizing, shifts have like pluses and minuses, reflections are times a negative, dilations are times a number. Besides that, we have to think outside or inside. Outside or inside. The addition subtraction tells us it's a shift, but where is the addition subtraction taking place from the function? Outside. And if it's occurring outside the function, it's happening to the y values. And if the y values are being changed, aren't the heights changing? Roughly,
Yes.
hang in there. The heights are changing. If the heights are changing, then it should be vertical. Does that make sense? If it's outside, it's happening to the y's. And if it's happening to the y's, then the heights are changing, which means it's a vertical shift. If it's a plus, it goes up. If it's a minus, it goes down, just like we would probably think, as long as we could connect transformation on the outside of vertical change. Addition, subtraction means it's a shift. If it's positive, it's going up. If it's negative, it's going down. Now, what would I say then for horizontal? If vertical is on the outside, what would horizontal be? It's on the inside.
Opposite land.
And it's not changing specifically the y values, it's changing, look at it, it's being added or subtracted from the x values. And if the x's are changing, that's going to be the horizontal change. And that trick is going to be true for all of them. If it's happening on the outside, it's vertical, inside, it's horizontal. But what's weird about horizontal ones? Right? Reverse psychology, something. If I see a minus, where am I actually going?
Right.
To the right. And if I see a plus, I'm going to the left, right? And if you wonder why, let me try to get to an example so I can kind of hopefully help some of you visualize, and some are like, I'll just memorize it, and that's okay. Totally fine. So we got it? Outside, inside? Outside, vertical, inside, horizontal. Outside, the way you would think, inside, a little funny. So what if I was to give you the following and say graph. Oh, come on, it won't be that bad. Hang in there. Choose a parent function other than a line.
Linear, x squared.
X squared. Other than a line. He was too excited. So let's do f of x is equal to x squared plus 4. G of x is equal to x minus 3 quantity squared. We're starting easy, right? Hopefully. If you need to graph a transform function, my advice is to always think verbally in the sense of identify what's really going on, how the parent function is being changed. How do we know the parent function on both of these is a squared? Take away the plus 4, what do you have? Take it down to its core, it's an x squared. Take away the minus 3, take it down to its core, what do you have? An x squared, okay? The parent function is an x squared, and what does an x squared look like? Parabola. Hold on. I'm running out of colors. Okay, a parabola. And what important points does a parabola have? 0, 0, 1, 1, 2, 4, right? That's one side. And on the other side, you see why maybe we did the points? It's a lot easier to talk about these parent functions in terms of a few key points. Instead of, let me not do it solid because that would kind of indicate the current graph. Let's do it dash to be like, that's the parent function. Now how does he change, right? That's the parent function. So what happens with that guy when I have f of x, the transform function, x squared plus 4? Verbally, describe it to me. Shift up 4, or a vertical translation by 4. Why? Because it's on the outside of the parent function, right? And how do I do that?
Shift it up.
Oh, you know, just take a point and like randomly move it up and say, meh, yay. That's not very precise. So how can we be a little bit more precise? Take the key points that we have and move them up one by one. So 0, 0 up 4 will now be 0, 4. 1, 1 up 4 will now be 1, 5, right? Just move the y's. 2, 4 up 5 will be now 2, 9. 5, 6, 7, 8, 9. Perfect. Then we come over here with negative 1, 1. Why am I training you for this? In homework, you are going to be given at least once. Are we okay? In homework, we're going to be given at least once a graph that has no function. You can't put it in your graphing calculator. You're going to have to just move the points in the appropriate way. Okay? And you're going to have about 8 different transformations, and you better try it. Okay, come back. How do I graph the other one then? So first of all, we got that for the up. And then for the next one, move it over to the right. 3. So a horizontal shift. Why? Because, sorry, my color coding. It's on the inside. Remember, it's backwards what we think. So it's a minus. We're going to move to the right. We'll talk about why in just a second. But then we come to our graph. Let me just keep it red. And then shift 0, 0. Now it's going to be 3, 0. Yeah? Only the x changes, not the y. I can't talk. 1, 1 is going to shift to 1, 4. Because the x, see, sometimes even graphing points gets hard. 4, 1. See how I'm switching my x's and y's? It's a struggle. Not because I'm bad at math, just sometimes your brain's too full of higher things to think of the littler things. Detail matters. Now I have negative 1, 1. Move it over 3. So 2, 1. I have 2, 4. It's going to come over to 5, 4. And I have negative 2, 4, it's going to come over, add 3. So not only have I done my transformations, but I've also, thank you, man, preserved. Maybe it's for you, but, oh, not yet. So I've preserved the shape for the most part, and I've been able to demonstrate the transformation. Now, has anybody ever wondered why the minus ends up moving it right? Why does the minus 3 on the inside move it to the right? Not the squared, because if it's a plus, remember, it moves it left. That wouldn't make sense. Put a rubber band in my pocket. Why does it move it right? How did we get the point 0, 0 to begin with? Plug in a 0 to, wait, who's our parent function again? When we plugged in a 0, we got out a 0, true? What do we plug in now to get out a 0 with this one? Positive 3. If we plug in a positive 3, we end up getting the same result as if we plugged in 0. So we take the point from 0, 0, we move him to positive 3 and say positive 3 plugged in will end up with the result of 0. It has that point. Same thing with, how did we get 1, 1 before? Plug in 1, get out 1. Sweet. What makes 1 now?
Minus 2.
Careful. Minus 2 minus 3 would be negative 5.
Plus 2.
What makes 1 now? 4. Plug in 4 minus 3. 4 minus 3 is 1. 4 will have the same result as 1 used to. Anyway, long story short, some of you were just wondering. Perhaps that helps a little bit. We're trying to make the old x's out of the new function. And in order to do that, we have to plug in positive 3. Positive 4. We have to plug in 3 more than the old x used to be. Anyway, let's stop. You guys like, that was the easy one. You just made him hard. Okay. Let's keep going. Let's not do dilations yet. They're yucky. Let's go to mirroring. Mirroring. Otherwise known as reflections. Thanks, Matt. Mirroring, otherwise known as reflections. The shape doesn't change. That's true. In the sense of my graph doesn't get distorted. However, what does change with reflection? Do you guys know?
All the points. Quadrants.
Not all the points. Kind of the quadrant. That's one way of thinking about it. Is there a snazzy word that talks about the way something is headed or going or facing?
Direction.
Direction, kind of. Keep thinking. A snazzier word. Computer people should kind of know this. I would think.
Vector?
It's not the vector that's going into physics a little too much. The way it's facing. The way it's directed.
Orientation.
Yeah.
Wow, you're nice looking.
Actually, I just.
Either way. The direction changes or the orientation changes. No judgment. I was about to give it. We got it. Orientation changes. The direction it's facing. Now, the tricky thing about this one, technically my outside-inside thing still works. But the problem is the wording makes it confusing in my mind. Technically, I think it was in your book last year too. If there is, remember reflections come about when there's a multiplication by a negative 1. If there's multiplication by a negative 2, then we separate and say, oh, there's a negative reflection, and there's a 2, uh-oh, dilation. And we split them up. So the negative multiplication by something negative results in a reflection. However, it's outside, right? And what did I say about outside? Vertical. Ah, sting, but look at the wording. What does it say? X-axis. Vertical doesn't go with x's. What's going on?
Let's go with
X-axis. If it flips in, otherwise, about the x-axis. Look, look, look. If it flips, what kind of flip is it doing around the x-axis? Hey, it's a vertical flip. My trick still works. A vertical flip is described as reflection in the x-axis, but you can just call it a vertical flip and I'm fine. A vertical reflection. And even though the book uses in, I'm sure there's some really snazzy mathematical reason why. I like the word about a bit better. In the x-axis, yes, that's true, and the book will say that. But I like the word about a little bit better. I think it gives the idea a little bit better. Doesn't mess up my squiggle. Okay, so how about the next one? It's on the inside. Inside we should correspond to horizontal flip. And why does that make sense? Visualize real quick the y-axis. If you are flipping yes, it says in. But if we change that to be about, and if you're reflecting about, think of it. That's a left-right reflection. What was on the right, left for you. What was on the left is on the right. What was on the right is on the left. So, my clues still work. On the outside vertical, on the inside horizontal. Reflections just mean flip. Now I think for the most part, most of you guys are probably okay if a parent function gets flipped. In the sense of, if a parabola has a negative on the outside, what happens? Where does it go? Yeah, it just goes down, right? Vertical flip. If the parabola has a negative on the inside, so a negative squared, it doesn't change. Oh, because a negative squared is a positive. That makes sense mathematically. Anyway, let's keep going. What if instead I was to give you something funny, like the following? Remember I said in homework, sometimes you'll have a graph with no function, just points. Let's say I was to give you -2, +1. -1, -2. 0, 0. 1, 3. And let's go 2, 0. Now let's to connect it. This is your parent function. This is a kind of easy one, hopefully. It's not too bad. The question, how would I graph? I'm going to write it in green. Hopefully you know why. In books, they usually name the normal one or the first one f. So let's call the first one, the first transform function g. And what if I was to name the next one h? And we call this one f. Think through the verbal description. What goes on if I have a negative on the outside? Vertical flip, right? So what am I going to do to all the points of the f of x? Flip the sign of, be specific.
It's y.
Vertical, y. Flip the sign of the y. How do I take what's on top to be on bottom or what's on bottom to be on top? I take the height and say, no, not up 1, down 1, right? And if I were you, I'd flip it one piece at a time. Not down 2, but up 2. Okay. Make it nice and smooth, unlike mine. Flip it, it stays the same, right? 0 times a negative is still 0. Then what? Instead of up 3, down 3, right? And then, 0 stays the same. Oh, there we go. What was up is down, what's down is up, etc., and we're done. Kind of makes sense using the points? Vertical flip, take the y's and multiply by a negative. So, the next one, verbal description of the transformation.
Looks like an 8. Sideways.
Infinity
sign.
Kind of. I don't know. Double helix? Anyway, so, an 8. An infinity sign, that's more fun. Stop. How do you describe the second transformation? Horizontal, because it's on the inside. You guys see why I had it red and green? Maybe you're not paying attention. I'm color coding the ones on the inside. I'm making red for horizontal on the outside, green, but that's okay. How do I do a horizontal flip? Change the x instead and keep the y. So instead of going left 2, I'm going to go right 2 and go up to that 1. Right? Instead of going left 1, I'm going to go right 1. Instead of going 0, 0, I'm gonna go 0, 0. There's no real flipping of him. And then instead of going 2 to the right, I'm gonna go 2 to the left. I missed somebody. Who did I miss? Oh, sorry. Instead of going 1 to the right, I'm gonna go 1 to the left.
This looks so nasty. Yeah.
Just wait until you get to the one in homework that has 7. Now hold on. Wait. Could I have drawn 2 totally separate graphs with the parent function and then changed it? Yeah. But was I able to save a little bit of time and use 2 different colors? What if there were 3? What if there were 8? Make a couple different graphs and pair up a little bit. Sound good? Get out of here, cool kids. We'll keep on going on Monday. Happy weekend almost. Hang in there with any quizzes or tests.
lines on one graph.
You can, but I'd rather be in different colors.
Okay, well, I have like 10 different.
Oh, well then you're good. Tyler, you're good to go.
It's gonna look like I just took a bunch of Skittles and like mashed them together. And then like,
Tyler, that's what my graphs look like
The
anyways.
air on it.
I actually, when I do my homework.
no,
I do
because
graphs.
yours is in black and white when you graphic table.
Fine, I use black and white M&Ms.
Somebody left their AP calculus book here.
Oh man, what are they thinking?
How many people are in your AP calculus?
30-ish period 1 and 32-ish period 6.
Oh, wow.
But BC 6.